Let's talk about linear momentum again. We talked about it last video, we introduced the concepts, but now we're going to talk about collisions. So when's momentum conserved? If we know that external forces cause a change in momentum, then when those external forces are zero, our change in momentum will be zero. So when can you apply it? All the time, in collisions. This is always true. Not always useful. If you've got external forces, you might need to do something a little bit different. And then you look at impulse, which we introduced last video. When can you apply conservation of energy? These are the two things that we're going to intertwine, momentum and energy. Well, all the time. You can always apply energy. Energy goes somewhere. We've been talking about that since day one. But when's it useful? It's only useful when you can track where all the energy goes in isolated systems. Sometimes energy in a collision gets lost as heat or sound, and if you don't know where it's going, conservation of energy isn't exactly helpful in that case. Let's talk about some cases where this is going to happen. By this, of course, I mean momentum conservation. So we've got a wagon, it starts to rain. No external forces, so the momentum of the wagon at the beginning, the momentum of the wagon at the end are going to be the same. At the beginning, you just have mass of the wagon times its initial velocity, but now you have the mass of the wagon plus whatever mass you added because of the rain. So we'll solve for the final velocity of the wagon, and we'll get this expression. This is how you get delta M. All I did was multiply my rainfall flux by the total amount of time. Now keep in mind, I am looking at the x direction. The rain initially has momentum in the y direction, but not the x. So px initial rain is 0, just because the rain's falling straight down. Now let's look at another example where we have a projectile. Projectile is going to pass through this block. So where are we going to start? Is momentum conserved? You betcha. Can you track all the energy? Well, no, because some of the energy is lost, making a big hole in the block, making it look less block-like. And we don't know how much energy is there. So we'll start with what we do know, momentum conservation. Always important to find your x-axis. Looking good. And then we know that the projectile has momentum at the beginning, it has momentum at the end, and then the block has momentum at the end. Our masses are going to divide out just because I put everything in terms of m. And then I'll solve for this final velocity, which is whatever initial velocity is divided by 8. All right, does that make sense? So conservation of momentum. I generally always start with conservation of momentum whenever there's a collision or an explosion. Explosions are just backwards collisions. But that will always work, and it's a good place to start. Now let's look at another example. So this example is a little bit different. We've got one ball going to hit another ball, and then they're going to take off in different directions. Now what we're getting at here is the idea that momentum is a vector. So we have to worry about x and y components. So initially, we're going to have momentum in the x and the y direction, and since there's no external forces, well, then momentum's conserved. Let's start with the x. The ball, big red ball, has momentum at the beginning, and it equals that. So then we've got to figure out, okay, we solve for the velocity 1 of x, and 1 is just the yellow ball. Cosine 30, we had to break that into components. I had to figure out what the final x component is. Right here, this is the final x component of that ball, because momentum is split. Okay, so now I've got an expression for v1 in the x direction for the yellow ball. Now we do the same thing. Initially we have no momentum in the y direction, and we have momentum at the end in the y direction from ball 1 and ball 2. I solve v1f. Oh look, this makes sense. Why is it negative? Well, because ball 1 went in the plus y, so ball 2 has to go in the minus y to conserve momentum. Again, we break this into components, break that velocity into components to get, that is py final for block 2. And you get the expression. You have an expression for the velocity of the yellow ball in the y direction and the velocity of the yellow ball in the x direction. And then you just add them together. Vx squared plus Vy squared equals V1 final. I hope that helps and makes sense. Please ask any questions in class, and I will see you there.